Hey everyone, and welcome to our next lesson in Unit 5. Today we're going to be learning about electron configuration, where we should be able to determine an atom's electron shell configuration after the lesson, and you will be able to draw Lewis dot diagrams once we are done learning about electron configuration. So before we get into that, we want to review a little bit of the basics. We know that each electron has a charge of -1, opposite that of a proton, which would be +1. And the mass is 1/1836 of an AMU. Since it is so small, we do ignore that amount of mass. And the proton number we know is equal to the electron number when we're talking about a neutral atom, and that's going to be equal to our atomic number. Now the electron configuration, which is what we're going to focus on today, we can find in an entry on the periodic table. In this case for fluorine, the electron configuration is 2-7, and that's an indicator of how many electrons are in each principal energy level, or what we call a PEL. Now, the PELs are going to change depending on how close we are to the nucleus or how far away we are. And the first principal energy level, which is closest to the nucleus, is going to be the smallest ring and therefore only holds a maximum of 2 electrons. The second principal energy level, the second one farthest out from the nucleus, would hold a maximum of 8 electrons. And as these rings get bigger, as we move farther out from the nucleus, they can hold more. So the next one further out, the third PEL, holds 18 total electrons. And as we get out to the fourth, and we can go beyond 4, they're going to hold 32 electrons. And these can be held or occupied in a further smaller category called a sublevel, which we don't get into too much here, but we'll talk briefly about what they are. But again, this is, if we think of our current model, sublevels are describing a more specific location for electron, which we know we can't actually pinpoint. And this will get us, if we go one further, right down to an orbital. We're going to be talking about those here momentarily. Now, a shell doesn't necessarily have to be entirely filled. So if we look at calcium, calcium's electron configuration is 2882, meaning it has 2 electrons in the first PEL, 8 in the second PEL, 8 in the third, and 2 in the fourth. Now, the first can hold a maximum of 2, so the first is full. The second can hold a maximum of 8, so that's full. But the third can hold 18, and right now we only have 8. So that one has electrons occupied in the third principal energy level, but it's not completely filled. And then we have 2 more electrons in the fourth principal energy level, which can hold 32. So we don't have to necessarily fill up one PEL before we start filling up the next one. And that's because our sublevels are going to fill at different times, and it doesn't necessarily depend on what PEL that it's in. And it has to do with the energy of the atom. And that's a topic that we no longer get into too much in our course. So this is the Bohr model of the atom, represented by Bohr's classic model of the atom, indicating that we have electrons that are lying in distinct energy levels around the nucleus. And they always show protons, neutrons, and electrons. So in the model here, we see that we have 20 protons and neutrons, or 20 protons and 20 neutrons, for a total mass number of 40, which we see here. Again, the 40.08 is an average of the different isotopes. This would be calcium-40, where we have 20 protons for our atomic number 20 and 20 neutrons. And then we can see how our electron configuration, otherwise known as Bohr notation, matches up. And that's going to correspond to each of our different PELs. First, second, third, and fourth. Now the first shell, the first PEL, has 2 electrons as far away as possible because of their opposite charge. Each of these electrons are negative, so they're going to want to separate from each other as far as they can within their principal energy level. The second shell has 8 electrons, which are going to be spread out as far as possible. Same thing with the third. It also has 8 spread out evenly and as far away from each other as they can. And the same with the fourth. We have our 2 electrons here in the fourth, which are spread out as far as we can get them in the diagram. Now going to our periodic table, if we look at elements that are in the same period, which is our horizontal row, in this case we're looking at period 3, they all have the same number of shells, meaning their electron configurations all have 3 numbers. And if we look at all of the elements in period 2, all of those elements are going to have configurations with electrons in only 2 principal energy levels. And if you look at the first period, you're only going to see 2 electron configurations for the 2 elements, either a 1 or a 2. Because remember that first PL can only hold a maximum of 2 electrons. So the period number is indicating the total number of principal energy levels in each of those atoms in that same period. And we can see that as we go from left to right, the last number here, 1, 2, 3, 4, counts all the way up until we get to 8, which will be an indicator that our valence shell is full. And we can see here with argon being a noble gas, all of our noble gases are going to have a full set of valence electrons. We'll talk more about that in a minute. So the valence electrons are only the electrons in the outermost shell, which we call the valence shell. So in each of these examples on the bottom here, the last number in the configuration is how many valence electrons that element has. So chlorine has 7 valence electrons. Argon has 8. They're completely filled in argon. Magnesium has 2. Lithium 1. Nitrogen 5. We don't worry about the other PELs, only the number at the end. So it's pretty easy to identify. We just look at one of the entries in the periodic table, and it's the last number in the configuration. So that's what we call a valence shell, which contains our valence electrons, and that's going to be important for our Lewis dot diagrams. Now, the number of valence electrons that a particular atom has are going to help determine its chemical and physical properties, because this is the part that's going to take place in bonding and interacting with other atoms. And we'll use these valence electrons to make the Lewis dot diagrams. So that's going to be an indicator of how many electrons are going to be available to or open for bonding or interacting with other atoms. Now there's a certain technique to doing this. You can kind of see here as we go down. This would be period 2. How we have carbon here, nitrogen, we see these dots kind of filling in as we go around, and they're increasing in amount from left to right because we have an increasing amount of valence electrons from left to right. So let's see how we're going to draw these. We're going to use dots and groups of 2 around the symbol of an atom representing an element, which is going to show us the valence electrons. And that's going to encompass our Lewis dot diagram. Now, electrons can be found in an S sublevel, a P sublevel, a D, or an F sublevel. And each of those sublevels hold a different number of orbitals. The S sublevel holds 1 orbital. The P sublevel holds 3 orbitals. The D sublevel holds 5 orbitals. And the F sublevel holds 7. Each orbital, if we represent an orbital by a flat line here, can hold 2 electrons. And these electrons like to be by themselves before they pair up. So when we draw these diagrams, the S electrons are going to fill up first, followed by the 3 orbitals of P electrons. So the S are going to fill in. We usually write these with arrows, which we would do for a box diagram, which we're not going to get into here anymore. And when we fill in our P orbitals, we're going to fill 1 electron in 1 orbital first, and then we're going to pair them up. And these arrows are representing the spin on the electron. And the electrons, when they're paired up, are always spinning in opposite directions for stability. So chlorine, to see an example of this, chlorine has in its valence shell 1 S orbital and 3 P orbitals, as we can see from up top here. Now, each orbital can hold 2 electrons. So chlorine has 7 valence electrons. And those 7 valence electrons are going to fill in these s and 3p sublevels. And the maximum number of valence electrons we can have are 8. So when we draw this, we have 2 electrons represented by 2 dots. 1 dot means 1 electron. And those are the 2 electrons in the s orbital, which can only hold 2. Now we have 3p orbitals. And when we draw these, we always put, just like we do with the arrows, 1 in each orbital before we pair them up. And then we can pair them up. So this would represent 7 electrons, 7 valence electrons around chlorine. And this one actually has another open spot right here. It still can hold 1 more electron, which is important because it explains a lot of why chlorine is so reactive, which we get into in our next unit. So these Lewis dot diagrams, looking at elements in period 2, again, period 2, all having electrons in 2 principal energy levels. So we have 2 numbers here. In our shell configuration, lithium only has 1 valence electron. So that's going to first fill in the s orbital. So we're going to show that on the top of the diagram or top of the symbol. Beryllium has 2 valence electrons. So those are going to fill the s orbital, maximum of 2. Remember, we can only have 2 per orbital, 2 per side of our symbol. Now, as we increase the valence electrons, now we're going to put an electron in the p sublevel, in one of the p orbitals, which there are 3 of them. So we see the first one filled here. And as we increase and move left to right across the table, we have an increase in the number of valence electrons each time. And you can see that we fill at 3 o'clock, at 6 o'clock, at 9 o'clock. 12 o'clock is already filled because that's the S, and we fill that one first, 1, 2. And then as we come down here, then we can pair them up once the 3, 6, and 9 o'clock are filled. So now we pair up, and when we get down to neon, which has 8, it is a full valence shell, meaning this is what we call a stable octet. Now, a stable octet means that all of the bonding sites in the valence shell, in this case for neon, are filled, and therefore it's not looking to fill any spots with electrons, which means it is chemically stable. It's completely satisfied. It doesn't really want to bond with anything. This is why neon and all of our group 18 elements, known as the noble gases, are stable, unreactive gases. So just to kind of reiterate how we're going to fill these diagrams, if we take our symbol, we're going to fill in this numbered order. 1, 2, 3, 4, 5, 6, 7, 8. And that's the order that we want to fill as we're filling our diagrams with different amounts of electrons. So we identify how many valence electrons we have, and then we're going to fill in this order. And that's really the extent of what we're going to do right now for Lewis dot diagrams. Now, the last thing I'll leave you with, a kernel is going to refer to everything underneath the valence shell of an atom. So it's including any electrons that are not in the valence shell and everything in the nucleus, protons and neutrons. And this is the part of the atom that isn't really responsible for any bonding or interactions with other atoms to make compounds. So we tend to not really refer to it because it's not really taking part in any of our chemical change. Now we know that the periodic table is arranged in order of increasing atomic number or the number of protons. So this causes the vertical groups to have a similar number of valence electrons. So if we look down any of the groups, they should all have the same number of valence electrons, meaning that any element in a vertical group is going to have similar chemical properties to the other elements in that vertical group. And that's due to the number of valence electrons, which is going to indicate how active or non-active they are in wanting to bond with other atoms. We'll expand more on the stable octet in our next lesson. Get this here. But basically, the stable octet means that the atom has a filled valence shell and is stable and not looking to bond with any other atoms to make any compounds. Make sure you guys come see me with any questions that you have, and I hope everyone has a great day.